Hello all, let us continue our discussion on high-speed designs. So in this particular video we will talk about the importance of Stackup, the build-up of Stackup, and the materials required for the laminate. So the first thing is, what is Stackup? Stackup is basically we can say a physical construction of a PCB shown in the form of different layers. So this particular PCB, if you see here, is made up of core and prepeg sections. So where core has the dielectric material, and then the copper layers above and below it, which comes as a ready-made material, which are stacked upon each other using a prepeg to form a stack-up. So this stack-up, while if you are working on low speed designs, definitely you need not consider much. You can follow the guidelines given by the PCB manufacturer and go ahead without too much of detailing. But for high speed designs, this stack-up plays a very crucial role. So especially how you arrange the signal layers, how you arrange the power planes, how you arrange the ground planes. So all these play an important role with respect to MIMC perspective especially, and also the impedance variations. So we generally route high speed designs in a strip line configuration, because that is where we can eliminate any radiations out of the board. And in this strip line also there are two things: how is strip line routing done with respect to the immediate layer above it and below layer. So if the immediate layer above it and the layer below that particular signal routing layer is a ground plane or a power plane, which means a continuous plane, then that is more helpful. So there is a simple pointer, but there are several considerations which need to be taken. So one important point here is that the high speed signals should be routed internally with a proper reference plane, and that's how your stack-up should come up. So there are several stack-ups that we use, whether it be 4 layer, 6 layer, 8 layer, whatever. So the image you see here is a 6 layer PCB. You can see here the top layer has a ground plane reference below, and then inner routing layer there is a nearest ground plane that is available, whereas the other routing layer has a nearest power plane as its reference plane. So we need to understand that the routing layer considers the nearest reference plane. Even though there are two reference planes, the nearest nearest plane is considered as the reference plane here. So the signals get the return path signals get routed to this power plane, and then the bottom layer has a reference of power plane. So this is how a simple 6 layer stack-up is built. Now, as we talked about core and prepeg, we mentioned that these are the two major sections of a PCB, right? So as we see here, there is a substrate, and then we have a copper layer on both sides, this is called a core, and at the bottom is another core, and these two cores are combined together using a prepeg. This is how construction happens. So the important point here is how is these substrates, if you see here, or the prepeg, are made of laminate materials. So these laminate materials are basically a combination of fiber and resin, and these laminate materials play an important role with respect to signal propagation. So now for a high speed design, it is important that proper selection of this laminate material is done. Any variation of these lamination materials could cause signal integrity issues for us. So now we will consider what are all the materials and why the laminate materials play a significant role, and then what are the properties of the laminate material to be considered. So as we mentioned, selecting the material, the laminate material, is a very important thing, important aspect in high speed designs. So because what happens is, if there are too many variations in the laminated material, when we say too many variations, basically the important property of laminate material is dielectric constant. So if dielectric constant is uniform in that particular laminate over its entire area, then the signal sees a common impedance. Now in high speed designs, impedance control is the important factor, right? So when we are doing this when we are trying to achieve this impedance control in the physical form, the PCB should also have an uniform dielectric constant across its area, so that signal sees uniform impedance. So that is where laminate plays a material. And as we are going into an era of 5G and also the other digital signals are increasing in frequency day by day, it is important that the laminate material is selected appropriately. Now what is that laminate material that is used, and why FR4 doesn't work here is basically for high speed designs the material used is PTFE. So why PTFE is used and why FR4 cannot be used is because of the higher variation of dielectric constant that we have talked in the previous slide. So what happens is, with FR4 the dielectric constant is higher, and also the variation of the dielectric constant over a given area is higher compared to the PTFE material. So that's why PTFE materials are preferred for high speed designs, whereas for FR4 this dielectric constant is varying over that given area. And now another important aspect is the losses. So the losses associated with FR4 are higher compared to the other materials used for the high speed designs. So example, if you see here, this is a simple view of ISOLA material. So there are different constructions based on the resin content. That is, we mentioned that laminate is a combination of fiber plus resin, right? So based on the percentage of resin content that is used, you can see here there are different constructions that are coming up. So 1080, 2113, we already heard about these materials, right? So you can see here over the given frequencies there is a variation of the dielectric constant, and also at higher frequencies we need the lower dielectric constant, but we see that the dielectric constant is higher at those frequencies. So we can clearly say that these specific materials shown here could be used only up to specific frequencies, and beyond those frequencies, because of this dielectric constant, we need other materials. And so the main important point we are saying, main important specification we are talking about when we are selecting material is dielectric constant, right? So here just as a reference, when you are talking about frequencies of 1 to 2 gigahertz, you can have a PCB dielectric constant around 3.5. Generally we know, right, FR4 it is 4.2. So as we go to higher frequencies it is 3.5, and if you are going beyond 10 gigahertz kind of frequencies, the dielectric constant required should be as low as 2.5 and below that. So that's how we need to select the PCB material, and there are several manufacturers already available in the market for this, like the ISOLA or the Roses, Taconic. All these have different PCB materials available. So we can say for a high-speed design engineer, PCB, bare PCB we can say, or the assembled PCB, which is made, we should say bare PCB, right? So the bare PCB which is made out of these materials is the biggest enemy, because we might have taken a good consideration in our circuit design to eliminate any reflections. We might have done simulations, and we might also have done pre and post layout simulations. In addition, we might have taken very good PCB layout considerations, but if the manufactured PCB has an issues of variation of dielectric constant, which is invisible, right? As a design engineer, you just get an assembled PCB and you have to work on it. So in such cases, it is very important that at the beginning phase itself, the design phase itself, the team talks to the manufacturing house, and also do some analysis required to come up with a stack up, to define the materials properly and give proper instructions to the manufacturer, so that they do not feel aftermath effects. So hope we gave a view of materials that can be used, or the properties that are important and how they affect in a high-speed designs. Please let us know if you have any questions. Please post your comments. Please like our video and subscribe to our channel. Thank you.